Bless you.
Okay, listen up. I told you that there were 3 scales or 3 things that are on the log scale that are used routinely. We've encountered the Richter scale. It's just powers of 10, right?
Yep.
Yeah. So if you want to find out how much more intense one was than another, then you just take the power of 10 for each of the Richter readings and divide them. Okay? We talked about that yesterday. You can have a question like that on your test. It's not very hard if you know what to do. The other one, another one that they use, which you've also had some experience with a little bit, is decibels. It's a log scale, but it's got a 10 on the front. There's a coefficient, and hence the deci part. But it's a log base 10. And the other one that is used routinely is the pH scale for acidity and basicness for generally fluid substances. Right? Okay? And here's a sample of it. This is the log scale for that, and it's got a negative on the front. For a good reason, which I'm about to explain to you. Well, pay attention here. This is the log base 10 of the number of hydrogen ions. That's how we represent that. It's a log scale based on proportions. You'll see in just a minute, okay? So what the question is, what we're going to ask is, which one has more hydrogen ions, vinegar or baking soda, and by how much? You're supposed to compare these 2 things. It says, I love the way they write this too. I want to tell you about this. It's funny. It says some especially sour vinegar has a pH of 2.4. And look, get this, a box of leg and sickle. What was that referencing?
Arm and Hammer.
Arm and Hammer. They didn't get the rights to use it, so they called it leg and sickle. You know, the hammer and sickle is on, usually put together. Hammer and sickle means hard work, productivity. It's also on the Russian flag. Yeah. So instead of arm and hammer, they chose the opposite or the counters of those leg and sickle. Okay. Anyway, leg and sickle baking soda has a pH of 8.4. So this is this acidic or basic? You remember your pHs? What's neutral? 7. This is acidic. This is basic. Can you think of any other substances that are acidic? Lemon juice.
Orange juice.
Orange juice?
Lime juice.
Lime juice. You guys are all citrus, aren't you? Hydrochloric acid. Battery acid. Most things that have acid in the name are, guess what? Acidic, yeah. Can you think of any other basic substances? Milk is a little bit basic. Water is pretty neutral. It depends on the water. But it's really close to neutral.
Bleach. Depends on the water.
Bleach.
So,
Bleach is the other common one. And maybe. I think it's more acidic. My mom, not knowing any chemistry, dang near made herself go bonkers.
oh,
Yeah, I've got it in my family. Yeah.
oh boy.
We have white brick on our house where I grew up because I'm about this high, and then there's paneling up, siding up from there. And there's this gigantic picture window out front that comes right down. The brick comes out like this, and it frames the picture window, comes back up, and there's brick underneath there. And it always gets sprayed and splashed on the dirt from the sprinkling system. The dirt, or the brick does. And my mom is worse than me, if you can imagine, at making sure things are cleaned up, straightened up, and all that kind of stuff. So she thought vinegar is really good for hard water spots on windows. And bleach is really good for whitening things like white brick. So she decided she'd kill 2 birds with 1 stone. She put them both in the same bucket. Yeah. Get too close to that. It's dang good thing it was outside. Because the ventilation was good enough. But she started going loopy. She started coughing really bad. Everything. You don't mix acids and bases. They combine together and form not table salt, but salts. That's what they call them, salts, like Epsom salts is made that way. And there's other kinds of salts that if you breathe the reaction that's creating the salts, it'll kill you. Yeah.
But was it treating you good?
Well, she was outside, and it started making her go funny. Well, anyway. As soon as she got away from him, she didn't have to go to the hospital. As soon as she got away from him, she was fine, but her lungs were trying to process this
So then what did she do?
gas,
How'd she dump it out?
mustard gas. What?
How'd you get
How'd you dump it out?
She did, we just got it away from her and then we, I don't know, probably put it in the irrigation ditch or something.
Did you come back and it was like?
Probably dumped in the driveway. The driveway's full of gravel and rocks, so it just kind of sucked. But, yeah, she was just trying to do two things with one, and they were having to be very acidic and basic, and mixing them is not a good idea, so be careful with that. Okay. Shh. Here's how we use this log, this pH scale, which is fixed up with logs. Here's how we figure out what's really going on. I'm going to consider that vinegar. The pH is 2.4, so that's what I'm going to replace pH with. Okay, and so far you may not have an inkling of what's going on here, but that's all I did is replace what the pH is. Now I want to figure out how many hydrogens this thing has, or at least a proportion of hydrogens. Okay, so first thing I'm going to do is divide both sides by a negative. I'm trying to solve for this. So now I've got this log equation. I've got the log isolated. Now what do?
Turn it into an exponent.
Thanks. Change it to an exponent. How does that look?
H T.
No, 10 to the
10.
negative 2.4.
To the negative 2.4 equals, and I know you were going to start H plus. That's fine. That's what it equals. But you wanted to start out with the H plus. I want to finish that way. So we okay on that? Now here's what it means. This is the reason why the negative on this is so important. This doesn't actually count hydrogens. Because if it did, you'd have 10 to the negative 2.4 hydrogens, which means you've got a very small fraction of a hydrogen. That's dumb. You don't have fractions of hydrogens. What you have here is this, folks. What is 10 to the 2.4, by the way? Positive 2.4, please. Positive 2.4.
251.1.
That's good. I don't care about the rest. But the 251 is what I'm interested in. This, because 10 to the 2.4, if I put that downstairs, it'll be 10 to the 2.4. So 1 over 10 to the 2.4 is 1 over 251 equals hydrogen. Hydrogen ion concentration. This is all about a concentration. It's about, what we're saying here is that for every hydrogen ion in this mix, there are 250 molecules that are not hydrogen ions. So 1 in every 250 molecules is a hydrogen. Okay? This is a concentration of hydrogen. Hydrogens to others. You with me? Now, let's do it for baking soda. We end up, can I come down to right here with the baking soda? I have 10 to the negative 8.4. You understand that's how it's going to work out? You know, I don't have to put it here. It's solve out the same way. Equals the hydrogen ion concentration. This is a concentration. This is not the number of hydrogens. It's the concentration of hydrogens in this thing. And that's going to be 1 over, somebody take.
251. Oh wait, no, 2,511,000. Oh no, it's
Give me one digit at a time.
Okay, 2511,88643.2.
Wow. This says that 1 out of every 251 million molecules is a hydrogen. Which one has more hydrogens?
Definitely the vinegar.
It says way more hydrogens because the concentration is much smaller, if you will. 1 out of every 251 is a hydrogen here. 1 out of every 251 million is a hydrogen here. Okay, that's the reason why it has to be a log scale, because the difference between this number and this number is too hard to try to work with when you're doing calculations and stuff. If we have a log scale, then the difference in magnitude is the difference between 2.4 and 8.4. That's not hard to work with or deal with. But it's a log scale because they are so vastly different from one another size-wise. So what's weird about this is because of this negative right here, the smaller number actually has way more hydrogens. The larger number has way fewer hydrogens because it ends up being a denominator comparison as a power on 10. You following me? Or not?
Yes.
Okay, so this is a hydrogen concentration. Not a number of hydrogens, concentration. Keep that in mind. That's what the negative does for you, is gives you a fraction to compare. Okay, next thing I want to talk to you about is it is a log scale, but it's not a, it's a natural log one. Having to do with this thing right here is called Newton's law of cooling. And this has to do with how things either cool off or warm up in a different temperatured environment. I mean, I'm talking about like when you take a cake out of the oven and let it sit for, you take it out of the pan or serve, right? Or like with little Miss Ellie, when I make her some mac and cheese, I do not take it right out of the pan and hand it to her. I either let it cool off a little bit stick some ice in it, pour a little milk in it, something, cool it off, because you can't serve it out of the pan. It takes a while to cool to the room temperature, or at least on its way cooling to there to where it's edible without burning, right? It also is true for things that are warming up. You take something out of the freezer, you don't want it, if it's ice cream, you don't want to leave it too long, it's gonna go runny on you. Right? So it has to do with approaching the temperature of the medium that you're sitting in. So listen, shh. This is the temperature of whatever's cooling or warming. It doesn't matter. This thing's constantly changing. This thing is constantly approaching the room temperature as little t, which is time, moves along. As time is allowed to move forward, this thing keeps changing. This is the changing one. This is a constant. This is the temperature of the medium. If it's in a room, probably 68 to 72 degrees Fahrenheit. That's the air temperature that it's cooling in, whatever you took out of the oven. This is the initial temperature. This was the temperature of your oven when you took it out. That's the temperature of the food by then. Because while it was in the oven at that temperature, it warmed up to there. So now it has this when you take it out. And again, we use the surrounding medium again. This is time, and this is a constant based on whatever's doing the cooling. And that is based on whether it's a bread, like a cake, or ice cream, which is a different consistency, or human tissue if you've died and are cooling off. Ooh. They use this in a CSI situation a lot. They come in and they say they see a dead body there. They take the temperature of the room, and they're going to make an assumption that that room has been that temperature since the body died. And then they take, it's actually truly a meat thermometer. It's about this long. It's got a probe about that long. Guy's dead. They're not going to hurt him. The end of those meat thermometers are kind of dull. But they just punch it in there until it goes through and goes into the liver. So your liver is your internal body temperature. And they know this value for human livers so that they can tell how long the body's been dead. Now, in a problem that you're going to do, the problems you're going to do, they will either tell you what K is, or you'll have to go find it first before you can make any other predictions. I'll show you how that works. It's coming up. So here's example 8 on page 327 if you want to listen at all. Sorry, not listen, but pay attention to what we're doing. If you want to read the words and see how it all works out. It says, in an experiment, a temperature probe, that's a thermometer, people. Or a meat thermometer. A temperature probe connected to a calculator-based laboratory. You actually have those. You plug them into a calculator, and you can hook the thermometer to your calculator, and it will take a data point every so often from the thermometer as time goes along. Okay? It was removed from a cup of hot coffee and placed in a glass of cold water. Shh. The first two columns of table 3.23, that's in the upper left corner of your page, show the resulting data for time t in seconds since the probe was placed in the water. The temperature T in degrees Celsius in the third column, In the third column, the temperature data have been re-expressed by subtracting the temperature of the water, which was 4.5 degrees Celsius. What is all that? Okay, listen, I want to talk to you about this equation for a minute before we reread some of this and you can understand it better. Listen carefully. Do you remember dealing or having an equation that looked like this that you've dealt with so far? Has anybody done anything like that yet with the homework you've had to do? Or maybe this. Or maybe this. Yeah? This is very similar to these, except for it uses E for a base, and there's an extra piece in here. But that's because we're doing a natural growth or decay. They put a Y and not, and this is pronounced Y not. It means the initial amount. We could put an A here. That'd be just fine. In all of these cases, A is the initial amount. Okay? The thing we're multiplying here has a base other than E, and here it has a base based on a rate per time, like 4% per year or something like this. So this has to do with a rate per time. You have to add it or subtract it from 1. This might be like the half-life stuff that we did where you put a 1/2 here and you raise it to the T over whatever the half-life is. Remember that?
Yes.
Recall that at all? This is a natural growth or decay process that is related to this. But I want you to look at I want you to compare these two. This is really Y, and this is really A. And you're going, what do you mean? Cooling, things that are cooling off are completely related to the initial difference in temperature. Not the initial temperature, the initial difference between the temperature of your item when you began the clock and the temperature of the stuff it's cooling in. That difference is your initial difference. This is the difference as time moves along. So this is like saying, here's the initial amount of stuff. This is the amount of stuff as time moves along. You see how they're kind of related? This is your beginning amount, but it's a difference of two things. This is the difference between those two things as time moves along. This time. So it's very much related to this. So let me read that last part again. It says, look at your table, by the way. Your table's at the top of page 327. Look at it while I read this. Everyone. You need to see this data and why it's presented the way it is for this problem. It says, in an experiment, the first two columns of this table will show the resulting data, the actual data collected for little t, which is time, in the first column, and the actual temperature of the coffee as it moved along. But we don't want the actual temperature if we're going to use an exponential function. We want the difference in temperature. We need the initial difference or the difference in temperature as time goes along. So you see that third column is T minus Tm. That's the Y value. T minus Tm is the Y value when we go to regress this data in our calculators. You got to understand that we're looking for a difference here, and that third column is the Y value, not the second column. The second column is used to generate the third column, but the third column is the Y value. This is your initial amount, and this up here is, it's going to make it cool off. That's the part that is a lot cooler. Now, I want to show you something really cool about your calculators. If you were doing this with a laboratory thermometer hooked up to your calculator, I'm not going to get the TV out to show you this, but just, this is something your temperature and your time by that little thermometer would have been dumped into list 1 and list 2 automatically. You've got to dump it in here now because we don't have that thing back, laboratory thing. So go to stat and please don't do any more than this. Just put the first and second column in because this is what would normally happen. First and second column. And list 1 and list 2. Got both lists built? Both of them are the same length? Okay, now here's what I want you to do. And I'll show you this when I'm done, those of you that are up here. But I'll build those first two lists. Now I want you to go over to list 3, and I want you to actually go up one until list 3 is what's being highlighted. So you got the blackened list 3. Are you there? You see the bottom of your screen says list 3 equals? When you have that highlighted thing up on list 3, you're able to define list 3 as something new. And here's what I want to do. Isn't that third column the temperature in the second column minus 4.5 because that's what we're cooling the temperature probe in? Okay, so just go like this. Go list, second function, and list 2 minus 4.5. And hit enter, and it will populate the entire thing for you. And every number will be 4.5 less than the one on list 2. So that's kind of cool. Yeah, when you highlight list 3, you're saying define list 3 to be list 2 elements minus 4.5. It'll generate them all for you, so you have to do it. So then we go back to
go back to regular, then do you just re-highlight it and then just put list 3 and redefine it as just list 3? If we want to get it back to normal.
Okay, that's good.
What do you mean?
So like, let's say we need to do list 3 for something else, but we don't want it to be just that list 2 minus 4.5.
Yeah.
You just clear it.
Yeah. Yeah, it won't define it that way all the time. Just until you double it. Okay, everybody clear so far? Now listen, shh. What we want to plot is this T, which is list 1, right? That's time. We want to plot list T versus list 3, because that's our Y value. To do that, you gotta make another change. Either that or choose a different plot. Now I need you to set up your plot. Hope you can understand what I'm doing on here, on you guys watching. You gotta go to, see the blue words right above your Y equals key? That's where you set up plots. So go second and the Y equals key. And notice that your plot 1 says scatter plot, list 1, list 2, box. Does yours say that?
Go second ways.
When number 1 is highlighted, if you look across there, it'll say that it's going to plot a scatter plot. That's what the little graph with all the little shotgun spots on it look like. And it'll use list 1 and list 2. Mine says list 3, those of you looking at this, because I've already adjusted it. We want to compare list 1 and list 3. So the way you do it is you hit enter and go into plot 1. Down there where it says Y list, go down there where it's highlighted and hit second and the number 3, because it's 1 and 3 we want to use for this plot. You see that? Now, let's go set up a window. Now that we got our plot set up, go to the window. The X's, which are the time values, go from 2 to 30. I'm going to go from, so that I can see the axis, I'm going to go from -5 to 40. 5 5s. For the Y's, remember the third column, they go from 7.5 up to 60.3. I'm going to go from, since my Y values, I want to see the bottom of my screen. I'm going to go from -10 to 65.
On your Y's?
5 5s. Yep. You see where I'm getting this from? Now, go back to your Y equals and turn plot 1 on and erase any equations in there that you have. If you've done it right, it should look like this.
Yep.
Like that. I don't know if you can see it very well, but it should look like that. Everybody got that? What sort of a regression do you suppose we're going to do with this?
Exponential.
Exponential, because that's what we're dealing with.
What I'd say is,
So go to stat, calc, and exponential regression, which is 0 at the near the bottom, and do your list 1, list 2, and all that stuff.
Or would it be list 1?
Save it in bars. Save it in bars 1.
Would it be list 1 and list 3?
Wait,
Oh
what
yeah,
regression?
you're right. You screwed up.
we're doing exponential regression.
Yep, it's got to be list 3.
Second one, second with 3. Yep. Bar.
Already there. Got it.
97%.
Dang, 161.
Oh, really? 179.
What do we get for the A part? What is the equation?
61.656.
656?
Yeah. Times 0.9277. To the X.
To the X. That's not quite like what we have here. Okay. So now is where you got to really think. If you haven't thought before, you got to think now. So the question asks, estimate the temperature of the coffee. How hot was the coffee? Here's what happened to the guy, and this is what I anticipate happened. Some guy was in chemistry lab, was asked to do this very experiment, and they gave him very, very specific instructions, which they didn't follow. So here's the coffee. Here's the water that we got a temperature probe in there, and it's gone up as high as it's going to go, and then we take the temperature probe out and put it in here, right? And you're supposed to start the clock right when you do that. Well, his lab partner was busy talking to some girl or something. And the guy put that in there, and he goes, hey, start the clock. And he goes, oh, crap. Shit, how far was I before I started? He goes, let's say 2 seconds. I put that on the lab chart. So they didn't get a 0 marker. The first one they took was 2 seconds. Do you suppose that temperature has cooled at all in 2 seconds? Yeah. Absolutely it has, because it went from a hot cup of coffee to nearly ice water. And in 2 seconds, that thing's going to start dropping. And they missed it. So the question that the author's asking us to find is to estimate the temperature of the coffee. That means we have to find the initial temperature.
0.
Is it this? No, this is the initial difference. That's this. This is the initial difference. So what was the initial temperature?
You plus it to that.
Plus what?
4.5.
Yeah.
Oh my gosh.
Just add 4.5 to this.
You do it once for a second.
Just once, because we only want the initial temperature of the coffee. We want to know how hot the coffee was. That means, what was the temperature probe reading when time was 0? It doesn't say on our table. But from this regression, we are able to tell, because this is the initial difference in temperature. And if this is 4.5, then this initial temperature's got to be this plus 4.5. Y'all see it?
Yes.
Okay. So what is that plus 4.5?
Wait. That's not a real number though, is it? Because it's got that X in there?
Why you just ask
You're getting
this?
carried away,
Just-
Mr. Brunson.
Oh, so it's just like.
So the initial temperature was 66.16. Right? Because this is the initial difference. So the initial temperature, what's really going on is we're saying T naught minus 4.5 is equal to that initial difference, 61.656. So add that to it. The initial temperature is 66.16. Did you catch that? Oh no. I would hate coffee at 66 degrees, even if I drank coffee. But if it's Celsius, that's a little warmer. Okay? That's pretty hot.
Iced coffee.
The other question asks this. See if you can figure this out with me. The next question says, estimate the time when the temperature probe reading was 40. When the temperature probe reading was 40. How are we going to figure that out?
Used to use
Yes.
Y2.
We could. Let's see what that does. If you go to Y2, what are you going to put in there? Okay, do that. And graph it. You'll graph the curve and graph the line. And then you find the intersect, right? Calculate an intersect. 5.76. That is not correct. The answer is 7.36 seconds. Why?
Because we're using the wrong equation.
Yeah, well, no, you're using the wrong idea because the temperature of the coffee was 40. But the Y value is 40 minus 4.5.
Plug in like 34.5.
Yeah, you got to take the 40 minus that because these are the Y values. This difference is the Y values. All they gave you was this piece of it. So what we're saying is 40 minus 4.5 is the Y value we want to test this at, isn't it? It's not 40. The Y value we want to see how long it took to cool to 40 is this Y value.
Oh my god.
So it's going to be 35 point or 45, 35.5, I think. Isn't that difference? Put that in your Y equals screen
Oh my god.
instead. I got the right answer.
Not 7.73.
Jeez, what calculator?
You get 7.73.
Calculate
34.5.
35.8.
7.355.
7.35. 7.36. And that's what the book says it is. And that's correct. Because you got to remember very clearly when you're using Newton's law of cooling what Y is and what A is. They're both differences. So you have to be very careful what they give you and how you use it. Okay? We are not going to do logarithmic re-expression. That's for people that don't have a calculator. Okay? So, you have now had the last of the lecture. Is that in here from the book? I still got more to tell you later, but we're done with the book. And I hope you all liked that. You all get to do this when you get back. I can send you a picture of it, Olivia, if you want. Bye. She's always texting me, can you send me a picture of the homework?